Imagine the universe is a giant flat sheet of paper. To get from one side to the other, you have to travel all the way across the surface. That's how we think about space travel now, a long, long journey across vast distances. But what if you could just fold the paper? You could bring those two distant points right next to each other. Now, imagine poking a pencil through both layers. That little tunnel you just created is a wormhole. It's a theoretical bridge, a shortcut connecting two separate points in space-time. This idea comes straight from Albert Einstein's theory of general relativity, which describes how gravity can bend and warp the fabric of the universe itself. The reason we get so excited about wormholes is because they represent a solution to one of our biggest problems: distance. The nearest star system, Alpha Centauri, is over 4 light-years away. With our current technology, it would take tens of thousands of years to get there. The Andromeda Galaxy, our closest galactic neighbor, is 2.5 million light-years away. These distances are so immense they feel impossible to cross. A wormhole changes that entire equation. It offers the possibility of not just reaching the stars, but doing so within a human lifetime, or maybe even in just a few moments. It's the ultimate cosmic game-changer. This concept fundamentally alters our place in the cosmos. Right now we are confined to our tiny little corner of the Milky Way galaxy. We can look out at the billions of other galaxies, each with billions of stars, but we can't touch them. They're like beautiful paintings on a distant wall that we can never get close to. If wormholes were real and we could use them, the universe would suddenly become our neighborhood. We could explore alien worlds, study distant stars up close, and perhaps even find out if we are truly alone. The thrill comes from the idea of transforming from passive observers into active explorers of the universe. Of course, these are all just ideas for now. Scientists have never actually seen a wormhole. They exist only in the complex mathematics of Einstein's equations. These equations tell us that such structures could, in theory, exist, but whether they can form naturally or if we could ever build one is a completely different question. It's one of the most fascinating puzzles in modern physics. The thought that we might one day build these bridges through space-time is what keeps astronomers and physicists dreaming. It's what drives us to look deeper into the mysteries of the universe, always asking, what if? The most immediate and profound impact of functional wormholes would be on space travel. Think about it. A trip to Mars, which currently takes about 7 months, could be reduced to a matter of minutes. Journeys to the outer planets like Jupiter or Saturn would be like taking a quick bus ride across town, but the real revolution would be interstellar travel. We could visit planets orbiting Proxima Centauri before our lunch gets cold. The entire galaxy would open up to us. Imagine sending probes or even people to the galactic center to witness the supermassive black hole Sagittarius A** from a safe distance. The age of exploration would be reborn on a cosmic scale. Beyond just traveling, wormholes would completely change how we communicate across space. Right now, sending a message to Mars takes anywhere from 4 to 24 minutes, depending on the planet's positions. If we had a colony on a planet orbiting a star 100 light-years away, a simple hello would take 100 years to get there, and another 100 years for us to receive a reply. That's not a conversation. It's a message in a bottle thrown into a cosmic ocean. With a wormhole connecting Earth to that distant planet, communication could be instantaneous. You could have a real-time video call with someone light-years away. This instant communication network would create a true galactic civilization. Colonies on different star systems could share knowledge, culture, and resources in real time. A scientific breakthrough on one world could be shared with all others immediately, accelerating progress for everyone. Governments could coordinate across star systems, and families could stay connected no matter how many light-years separated them. The isolation of deep space would disappear. Humanity would no longer be a scattered collection of isolated outposts but a single interconnected society spread across the stars. This would be as significant as the invention of the internet was for us here on Earth. This revolutionizes not just how we talk but what we can learn. We could place telescopes at the other end of a wormhole, giving us a view of the universe from a completely different vantage point. This would allow us to measure cosmic distances with incredible accuracy and get a 3-dimensional map of the cosmos. We could study the early universe by pointing a wormhole toward a very distant region, effectively looking back in time because of how long the light took to travel. The scientific possibilities are mind-boggling. Wormholes wouldn't just be a mode of transport, they would be the ultimate scientific instrument for understanding the universe. The idea of wormholes gets even stranger when we consider their relationship with time. According to Einstein's theory of relativity, time is not constant for everyone. If you travel very fast, close to the speed of light, time slows down for you compared to someone who is stationary. This effect is called time dilation. Now let's apply this to a wormhole. Imagine you have a wormhole with two ends, mouth A and mouth B, both located here on Earth. You could keep mouth A stationary and take mouth B on a round trip through space at nearly the speed of light. When mouth B returns, less time will have passed for it than for mouth A. What happens now? Mouth B might be 1 year in the past relative to mouth A. If you were to step into mouth A in the year 2050, you could emerge from mouth B in the year 2049. You would have just traveled back in time by 1 year. By manipulating one end of a wormhole in this way, it might be possible to create a bridge not just between two places in space, but between two moments in time. This opens up a whole can of worms, leading to paradoxes that have puzzled scientists and philosophers for decades. What if you went back and prevented your own parents from meeting? It's a fascinating but deeply problematic idea. Many physicists believe that nature would have some way of preventing these paradoxes. There might be some unknown law of physics that stops a wormhole from being turned into a time machine. For instance, the very act of trying to use a wormhole for time travel could cause a massive feedback loop of energy that would instantly destroy it. This idea is called the chronology protection conjecture, a fancy way of saying that the universe protects its own timeline. It's as if the cosmos has a built-in safety feature to prevent us from rewriting history and causing logical contradictions that would unravel reality itself. So, while the mathematics suggests time travel through wormholes might be possible, it remains highly speculative. It's an exciting thought experiment, but it's far from a proven scientific concept. The risks are enormous, and the physics is on shaky ground. For now, we should think of wormholes primarily as potential shortcuts through space. The time travel aspect is an intriguing side note, a reminder of how much we still have to learn about the fundamental laws of the universe. It shows us that when you start playing with the fabric of space-time, you might get more than you bargained for. Even if we ignore the mind-bending possibility of time travel, just creating and using a stable wormhole for space travel presents monumental challenges. First and foremost is the problem of stability. Most scientific models suggest that a wormhole would be incredibly unstable. The moment it forms, it would likely collapse in on itself faster than the speed of light. To keep it open long enough for something or someone to pass through, you would need a special kind of substance with very strange properties. This substance is often called exotic matter, and it would need to have negative energy density, which is a way of saying it has anti-gravity properties. The problem is, we have never seen or created exotic matter. It's purely theoretical, and the amount of it we would need is staggering. To create a wormhole just 1 meter wide, some calculations suggest you would need an amount of negative energy equivalent to the mass of the planet Jupiter. Harnessing that much energy, let alone negative energy, is far beyond anything we can imagine today. It would require a level of technological mastery that would make us a truly advanced civilization, capable of manipulating the energy output of entire stars. So, the energy requirement alone is a huge barrier. Then there's the question of how you would even begin to build one. Do you find one that formed naturally out in the cosmos? Astronomers have never detected anything that looks like a wormhole. Or do you create one from scratch? This would likely involve manipulating gravity on an unbelievable scale, perhaps by using a black hole. But black holes are the most destructive forces in the universe. Trying to engineer one to create a wormhole without getting torn apart by its immense gravity would be an incredibly dangerous undertaking. The engineering challenges are just as daunting as the physics problems. Finally, we have to consider the safety of traveling through one. Even if you could build a stable wormhole, what would the journey be like? You might be exposed to intense radiation or extreme gravitational forces that could rip you apart. And what if the wormhole closes while you're halfway through? The list of potential dangers is long. For all these reasons, wormholes remain firmly in the realm of science fiction for now. They are a beautiful and inspiring idea that pushes the boundaries of our imagination, but they are also a humbling reminder of how much we still don't know about our universe.